Experimental design often starts with a conflict between unique project requirements and rigid templates. Many standard designs demand a set number of runs or specific factor levels that may not align with your actual resource budget or process complexity. Instead of forcing your parameters into a prepackaged box, JMP's custom design platform gives you the control to engineer experiments tailored specifically to your goals. We are going to explore 5 distinct experiment types using custom design: screening, response surface, mixture, covariates, and randomization restrictions. Correctly defining the factors and constraints of your environment produces a design built specifically for your project. This approach creates experiments that are statistically robust while remaining within your physical and budgetary limits. In the early stages of studying a process, you often have a long list of potential factors. The objective of a screening experiment is to isolate the truly active factors from the noise. To do this, custom design uses the D-optimality criterion to precisely estimate these main effects. This model panel displays how the platform handles potential interactions. Looking at the list of terms, you can see factors x1 through x5, followed by all their corresponding two-factor interactions, automatically categorized as necessary for the model. To balance your budget while avoiding the overlapping, or aliasing, of these main effects, you can dictate the exact scale of the experiment. Here, in the Design Generation section, the number of runs is user-specified to 16. Once generated, you can evaluate the design's validity. This color map on correlations illustrates the relationships between effects, with the diagonal black squares indicating where absolute correlation occurs. Often, physical logistics prevent you from running an entire experiment at once. If testing must be split across multiple days or shifts, you assign a specific factor, like x4 here, to the blocking role. Looking at the resulting generated design table, the x4 column successfully organizes the 18 total runs into sequential blocks. Identifying active factors early prevents you from wasting budget on insignificant variables, and organizing those tests into fixed blocks minimizes day-to-day operational variations. Once active factors are identified, the next phase is building a predictive model to optimize your settings. For this, we use a response surface methodology, or RSM design. When you select RSM, JMP triggers a system automation that shifts the focus from D-optimality to I-optimality. While D-optimality targets the outer extremes of the design space to find exact coefficients, I-optimality covers the central surface area. This minimizes the prediction variance across the entire space you intend to operate within. Real-world physical constraints also come into play. If your equipment physically cannot combine a low temperature with a specific catalyst, you program that limitation into the disallowed combinations filter before generating the design. Applying proper physical constraints within an RSM design ensures that the resulting predictive model is mathematically sound and viable to execute on the production floor. Mixture experiments are necessary when all your factors are ingredients that must sum to exactly 1, or 100%. The software allows you to blend these proportional mixture ingredients with standard environmental variables in the exact same model. This list shows chemical mixture ingredients like copper sulfate interacting directly with wavelength, a non-mixture process factor. You evaluate the reliability of a mixture design by analyzing its prediction variance. This fraction of design space plot maps that variance. As the line curves upward on the right, the prediction variance increases near the extremes of the design space. You can also construct nested mixture of mixtures designs. Think of separately mixing dry and wet baking ingredients before combining them. In the value section, you establish precise lower and upper limits for every subcomponent: the cocoa, sugar, flour, butter, and milk. Attempting to process these nested proportional constraints in standard templates usually results in mathematical singularities that crash the model. Custom design processes them natively. Sometimes you have pre-existing characteristics attached to your experimental units that you cannot change or control, like the specific gravity or tensile strength of a supplied material. These are covariates. To account for them, you use an existing data table. In the factors list, specific gravity, tensile strength, and supplier are explicitly defined as covariates. This tells the algorithm to dynamically select the optimal runs based on the available units. Explicitly logging these uncontrollable variables prevents unpredictable baseline variances from skewing the final analysis of the factors you actually can control. In industrial environments, certain settings are physically hard or very hard to change. You can't instantly cool a massive furnace for every trial. To handle these randomization restrictions, you use split plot designs. Because split plot designs group runs together, the model now contains random effects. Therefore, the required analysis method for these designs is REML. This parameter estimates table provides the initial statistical output. The red values in the probability column indicate which of your whole plot factors are having a significant effect on the response. To refine this, you create a reduced model. You systematically remove any factors that lack statistical significance and are not involved in two-way interactions. Reducing the model clarifies the data. Look at factor C2 in this updated report. By removing the noise of insignificant variables, we see that this hard-to-change factor is now clearly flagged as statistically significant. Properly mapping your factor change difficulty upfront prevents operational bottlenecks on the floor and guarantees accurate statistical readings in your final report. We have moved from isolating variables in screening to modeling boundaries in response surface, blending mixtures, accounting for covariates, and respecting physical limits with split plots. Across all these methods, the rule remains the same. Correctly defining your factor roles, constraints, and optimality criteria gives the software exactly what it needs to generate a highly optimized model. Open the sample datasets in JMP, set your parameters, and start translating your unique operational